Okay, when we last left our hero, he was talking about local linearity. Now, let me explain what local linearity is with a picture of a graph. Okay, what I've done here is I've graphed using Desmos.com. I've graphed a parabola whose equation is y equals 1/2 x squared, as you can see on the left here. And y minus 2 equals 2 parentheses x minus 2. This is that blue line. You can see this is the equation of that blue line in point slope form. Now, if you look at this, this blue line is tangent to this parabola at the point 2, 2. Okay? They touch at 2, 2. Now, at this point, looking at it from this perspective, this parabola totally looks different from this blue line. And as you can tell, the blue line, his slope or rate of change, it's always the same. It's always 2. Whereas we said with this parabola, if you're over here somewhere, on the left side of the vertex, you have a negative slope or a negative rate of change. Whereas if you're over here on the right side of the vertex, your slope would be a positive number. And the further you go away from the vertex, the steeper or the more positive that slope would be. So as you can see, the parabola's slope is always changing, whereas the line slope is always the same. So these graphs look totally different. But here's what local linearity says. What happens if I zoom in on this graph where the parabola and the blue line meet? Well, if I zoom in at 2, 2, watch what happens when I do this. If I start zooming in here, notice that the blue line and the red graph, you can still see there's a slight difference between them, but as I come into this point of tangency, we say, if I keep zooming in, at some point, the blue line and the red parabola, they look like they're one and the same. Again, let me zoom out. You can see that they're different, but as I zoom in, and I get really close to this point 2, 2, you can't tell the difference between the blue line and the red curve. So wouldn't that mean that really zoomed in, the slope of this red parabola and that blue line, they must have the same slope at that point of tangency? Now, again, as I zoom out from there, and I go back, at any other point on this graph, say this point right here, definitely this red curve, his slope is totally different from the blue lines. This red curve is much steeper. And if I go to the left side of the vertex, the slope on this side at any point is negative. It's got a negative slope, whereas we know the blue line slope is always positive. So, what does that tell me? Well, local linearity says that if I really zoomed in on the point of tangency, the point where the curve and the line touch, the slopes would be the same because, well, that curve looks like a line at that point of tangency, but only at that point of tangency. Now, the next thing, does it have to be a tangent line? What happens if I change the slope of this line to say -2? Well, right now this blue line looks really different from this red curve. If I zoomed in now, does it ever look like the parabola and the line become one and the same? No. As you can see, there's no way that that would ever happen. So we can never assume that the blue line slope is the same thing as the red line slope. So that tells me that, well, again, the slope can't be a negative number. I mean, it has to be that tangent line of 2 with a slope of 2. What happens if I had a slope of 3? Now that looks pretty close, but that doesn't look like a tangent line. That looks like it's crossing the graph at 2 points. Well, if I zoom in, does it ever look like that red line and the blue curve start touching? No, they don't, right? There's always that gap. No matter how much I zoom in, I always see that gap. So in this case, when I changed that slope to 3, that was no longer a tangent line. It was what we call a secant line, and that secant line slope was not going to be a good way of finding the slope of that curve at that point of tangency. At what was it? At 2, 2, right? So if I change it back to 2, 2, and I look at that, you can see that this curve and this tangent line have the same slope. Well, that's important. So that leads to this big rule, and that big rule says that the slope of a curve will be the same as the slope of the line tangent to the curve at the point of tangency. In other words, where the line and the curve meet. Okay, so let's take a look at how we can use that rule to start finding the slopes of curves, knowing that the curve slope will change. So look at this first example here. It says find the slope of the curve at the point of tangency. Well, in this first example, the point of tangency is right here at A. To find how steep this curve is, I'm going to draw in this tangent line. Now they've actually already drawn in the tangent line there for me. So now all I have to do is find the slope of this tangent line, and that'll be the slope of this curve at that point. Well, let's see here. It looks like from here to this point on the line, notice I'm finding the slope of the line, not the curve. The slope of the line will be down 1, 2, 3, 4, 5, 6, right? And you would go to the right one. So my slope of this curve would be -6 over 1, or just -6. For this one, at this point right here, the slope of this curve at this point of tangency would be the slope of this line. And if I wanted to count the slope of this line, I could go 1, 2, 3, 4 down and write 1, so the slope would be -4. And isn't it easy to find the slope of a line? Because we've been doing that since algebra, right? Now let's take a look at a positive example. Look at this guy right here. At this point of tangency, well, again, to find the slope of this curve at this point of tangency, I'm not going to focus on the curve. I'm going to focus on this line that's tangent to the curve at that point F. Well, it looks like to get from here to here, I'm going to go up 1, 2, 3, 4. So my rise is 4, my run is 1. So my slope of that curve is 4. And then lastly, going back to this curve, how about at the point 0? Well, again, if I drew my tangent line in here, wouldn't that be a horizontal line? And isn't the slope of all horizontal lines 0? So the slope of this curve at the vertex of this parabola would be 0. Okay, last example. All right, now we're going to have to do it ourselves. Now it says, in this problem, they're not drawing the tangent line for me, so I'm going to have to do it. So it says, estimate the slope of the curve at these given values of x. So the first thing I need to do is find the points where x equals -1. Well, at x equals -1, if I go over to -1, isn't my graph touching right there? So now I have to draw my tangent line to this curve at this point. So I'm going to come in with my tangent line, and let's see here. Now that's not really tangent yet, is it? But if I slide it around, does that look like a decent tangent line? I think it's okay. So now I'm just going to pick 2 points that I know on that line, which looking, I know, let's see, it looks like I know that point right there, and I know that point right there. So the slope of this line will be down 3 and right 1, 2, 3, 4. So I would say the slope of this curve would be -3/4. Again, if I did it at 2, so at 2, the point of tangency would be right there, coming in with my tangent line. It might look something like this. Is that okay with you guys? And now I'm going to pick 2 points that are on that tangent line, like right there, and say right here. And it looks like I'm going to go up 1, 2, 3, 4, and right 1, 2, 3. So in this case, my slope of my curve at x equals 2 would be 4/3. And then lastly at 0, well again, there's that, if you look at that example, it looks like my tangent line would just be a horizontal line, wouldn't it? Yeah. So if I came in like that, well, what's the slope of that line? It's 0. Okay? And I think you get it. All right, folks. I'll talk to you later.